Hello, welcome. This will be our last kind of major topic video in 334 this term. We're talking about recovering from a crash. What algorithm do we actually use? How do we use the write ahead logging discussed in the previous video to actually recover our data when our system goes down and we lose everything that's in memory. And as I said, this will be the last major topic. The final video will be a kind of overview of a number of major database systems topics that we didn't have time to get to in this term. All right, so to set the scene, let's again go back to our tried and true example. We have some transaction TI that's transferring $50 from account A to account B. And so we have two updates here. We need to do A minus 50 and B plus 50. And this transaction is going to require that these changes actually be output to disk, that they are persistent. We need the durability of our ACID guarantees. And we need both of them to be output in order to be consistent, that if we just subtracted 50 from A but didn't add 50 to B, then we would not be accurately, the database would not accurately reflect a consistent state of the world. And so a failure may occur kind of at any point here, that if we add in, we begin our transaction, we read A, write A, read B, write B, and commit. Kind of at any point in here, we could have a failure and lose everything that we have not written out to disk. And if we kind of don't modify, if we don't make all the modifications, then we might have an inconsistent state. If we only make, if we don't make the modifications, we've lost these updates. And so our recovery is going to consist of two parts. So the first part, which was the subject of our logging video, was doing some extra work during normal execution, and this was our write-ahead logging. And then the focus for today is going to be kind of part two of this, which is actions taken after failure to recover. So there will be a few parts of sort of this extra work during normal execution, which I'll need to get into to kind of complete the picture of what we're going to have in our log and on disk in order to ensure that our actions taken after the failure can actually get us to recovery. So just a brief reminder of what this write-ahead logging is going to do. We're going to have our log of log records, kind of each, and we're just going to be appending to this log, and we're going to keep this log on disk. And every time that we have an update, we're going to make an entry to the log. We're not going to log reads. There's no change to the database. We don't need to recover those. But updates or writes, we do need to recover. And so these are going to be of the form. We're going to have some transaction. We're going to record kind of which database object this update was modifying, and the old value and the new value. And so this would be if we had a write of x by ti that changed the value from v old to v new, we would make an entry in our log like this in order to record that this write took place. And the other two sorts of records that we're going to concern ourselves with that transactions will generate is just a start or begin record, as well as a commit record. And so these are the three types of records we'll see from transactions. And an important aspect of write-ahead logging says that we can't ever write pages that were modified out to disk unless the log records of those modifications are first written out to disk. So that's the write ahead. We always have to get the logs out to disk before we get the pages out to disk. And a transaction has truly committed when this commit log record is written out to disk. All right, so when we're doing our recovery, there are a couple different kind of operations that we're going to need to do. We're going to undo some transaction. We're going to need to be able to undo a transaction as well as redo a transaction. As you might imagine, undo is going to restore all our values that were modified by TI to their old values. And you can see how our log record of this form is going to be useful, that we know which object and we know what value we want to restore it to, the old one. And we know each of these records is also includes which transaction, so if we're undoing a particular transaction, we can pick out the records associated with that one. And as we'll see later, when we do this restoration, we're actually going to add additional records to the log to record that we undid some previous update. And we'll see how that works a little later on. For redo, we're going to want to replay history. We're going to want to set all we're going to set the data that TI would modify to the new value. So to redo some transaction, we're going through our log and saying, okay, this transaction updated some data, some database objects to this new value. We're going to reapply that update because it may have been lost when the system crashed. And there's no special logging that we do here. So when the database fails, how do we know which transactions we should undo and which we should redo? So for that, on failure, what we want to do is undo some transaction TI if our log contains the start of TI, but the log doesn't contain either a commit or an abort. So if we see a transaction that started but never finished, either with a commit or abort, we need to undo all its changes restore the database to a consistent state. That we want our transactions to be atomic, right? We want them to all of the operations they do to happen or none of them to happen. So if we have one that was kind of in the middle of its work when we had a crash, we recorded that it started but never any sort of completion, then we need to undo it. And we're going to redo transactions basically if we have the start and the commit or the abort. Now you might be asking, why would we redo a transaction that we know aborted? Isn't that kind of redoing operations that won't actually end up happening? We're just going to undo them as a result of the abort. And this is a potential optimization one could make to a recovery algorithm to try and be clever and identify the transactions that successfully aborted in the log and figure out, well, what identify kind of which things don't need to be redone. But if we just go through and redo everything to kind of restore the database to the state it was at the point of the crash, and then undo the things that we need to undo that didn't complete, that's going to greatly simplify our recovery algorithm. So potential optimization to be clever about aborted transactions, but we're going to go the simple route for now. So now I want to show you kind of some example logs and what it would mean in terms of applying our definitions of when we undo and when we redo. All right, so here we have three different examples where we have a T0 transaction that's doing a transfer of $50 from A to B, and a T1 transaction that's subtracting 100 from some account C, and we have three different cases where a crash occurred at different points. We have the crash occurred kind of in the middle of T0, in the middle of T1, or after both transactions. And so let's look at what do we need to do in each case. So we crash in the middle of T0. We see, okay, we have a T0 start, but no T0 commit or abort. So we want to undo T0. And so what do we actually need to do to undo T0? Well, we're going to read kind of backwards through our log, and we're going to undo each of the updates that we see. And as I mentioned earlier, when we undo something, we're going to add a record to the log to record that this has been an undone. This is a modification. Undoing this change is a modification to the database that we want to be persistent, and so we're going to put it in the log. So when we go to undo this first update, our old value is 2000, our account is B, so it says, all right, we want to restore B to the value 2000. So for this, we'd make that change and we'd add a record to say T0, we undid a change to B, and the value it now has is 2000. And this is what is called a redo only record. And because it's something that we're only going to redo and not undo. These are also called compensation log record, or CLR is another name, but redo only is very clear about kind of what the one purpose of this is, and if we continue going through this, I'll explain how why we want something that's redo only. So we continue going back. All right, now we're undoing the change to A, or restoring A to 1000, and now we get all the way back to T0 start. And okay, we know we've seen all the records from T0, we've finished undoing it, and we can then append T0 abort to the log, to record the fact that we now have successfully undone T0. And let's say at this point there was some kind of crash, and we come back, and we would then have a case where T0 started and we have it successfully aborting. So it's no longer something that we want to undo, it's a transaction we want to redo. And to redo this transaction, we would kind of read forward through our log, replaying the history, replaying the updates that it did. And if we hadn't recorded these redo only logs, in our replay, we would replay these two updates, and then they would never be undone. And so the one purpose of these redo only records is that then when if we have another crash and we're redoing this log, the rollback, the undoing of this T0 transaction is part of the log, and so gets applied to the database correctly. All right, so this is our example where we crash in the middle of T0. Now we crash, what if we crash in the middle of T1? For this, we are going to want to redo T0 and undo T1. T0, we can see, successfully completed in our log, so we want to redo it. T1 didn't, so we want to undo it. And we go through and set A to 950, B to 2050, and then in order to and we get and we replay or redo T1 as well. C is 600, and now we undo T1 to say, all right, T1, it's changed to C. We're setting it back to 700, and now we've gotten back to the start of T1, so we have successfully rolled it back, and we can add T1 abort to our log. And finally, in our third example, we have a crash after both T0 and T1 have committed. So in this case, we would want to redo both of these transactions. We go through the log, reapplying all the updates, and that would be that. So in each of these examples, we had a very short log. We could just look at a handful of records and know kind of what we needed to redo or undo. But in a real system, we might be processing dozens, hundreds, thousands, hundreds of thousands of transactions every second. And so we might have extensive logs and a situation where we crash and we need to go back to the beginning of time, the beginning of the log in the 2 years that we've been running this database at 1,000 transactions a second, and try and redo all of them. That would be, of course, an absolute nightmare. So what we're going to do is at regular intervals of some kind, and the frequency of these is an aspect of considerable kind of optimization or tuning to a particular database. But at regular intervals, we are going to take checkpoints. We are going to basically freeze the database and make sure that everything is flushed out to disk. So let me get into at least this first attempt at what checkpoints are going to be. So the main purpose of checkpoints is to tell us, all right, how far back do we need to look for data that we might have lost as a result of the crash. So the point of the checkpoint is to say, all right, from all the changes from this previous to this point in time, this checkpoint, you know those were written out to disk. You don't have to worry about recovering them because you lost the dirty pages that were in memory. So our checkpoint is going to is going to force all of our log records that are currently in memory to be output to disk. So when I say output here, I mean output to disk, to our durable storage. And second, we're going to, this might be clearer if I said, instead of output, write out all of our dirty pages. So we're going to get all of our logs out to disk, and then once those are there, we know that it's safe to write all those actual modifications that were only made in memory out to disk. So we'll go through our buffer pool, write out all the dirty pages. And third, we're going to write a special checkpoint record to our log. And this is to indicate in the log where a checkpoint happened. And this L is a list of our active transactions at the checkpoint. So this is transactions that had started previous to this checkpoint but had not yet committed or aborted. And we're going to need this list of active transactions to know which transactions updates might we need to redo or undo. And importantly, we're going to say that no updates are allowed to be made to the database during this checkpoint. We're basically going we're going to say all transactions, no new transactions can start. We're going to wait for all currently running transactions to stop, and then we're going to basically freeze the database while we go through and make sure that everything is durable on disk. And then once this is complete, we can allow transactions to start running again. So this kind of freeze the world assumption is a very strong one. It has significant performance implications, and in practice we could not afford to take checkpoints like that in a real system, but it will be a simplifying assumption that we make for now, and I'll talk later about how we might make checkpoints kind of less heavyweight and more practical for a system that needs to have availability, that can't afford to freeze for the whole time it takes to write everything out to disk. All right, so a little more about checkpoints. That this list L, as I said, is going to tell us the transactions that were currently running at the time of the checkpoint, and when we have a failure, we're going to scan backwards we're going to scan the log starting at the most recent backwards until we find a checkpoint record, so that here is where the last checkpoint was. Here are the transactions that will need to be redone or undone in this list, along with those that started after the checkpoint. So as we're scanning backward, if we see a transaction start record at any point while we're looking for this checkpoint, we know that transaction also will need to be redone and undone. And because our checkpoint is writing out all the data currently in memory, our log records and our dirty pages, we know that no transaction that completed before our checkpoint is one that needs to be recovered. As in, we know that all transactions that completed before our checkpoint are going to be on disk, And so we're only concerned with those transactions that were active, that hadn't yet completed when the checkpoint was taken, or ones that started after it. And to kind of see this in visual form, let's say that we have time on this axis here, and we have checkpoint at some point in time, and then our scary failure or crash at this point in time. And so if we're looking at the duration of some transactions, maybe T1, T2, T3, and T4, we can see that T1 we don't have to care about. It finished before we got to our checkpoint. We know everything's on disk. It's all good. T2 and T3. T2 is active during the checkpoint. T3 started after. Both of these so this we don't care. T2 we're going to need to redo. T3 we're going to need to redo because both of these actually completed before the failure. So we just want to restore their state. And finally our T4, which was active when the failure, it never got to complete. So to put the database in a consistent state, we would need to undo this one. And one key point that I want to make with this picture is notice that the transaction 2 that we need to redo, it started before the checkpoint. So in order to redo it, we would need to go back in the log to its start and replay all of those updates. And in fact, when we're doing recovery, we scan backwards to the checkpoint to find kind of all the transactions that we might need to redo or undo. But then we might need to go further back in the log to where the earliest transaction that we need to redo or undo began, and go from there. All right, so with all of this in place, now it's time to actually talk about what is the algorithm that we'll use to recover at this point of failure. All right, so our recovery is going to consist of 2 phases. We're going to have a redo phase and an undo phase. So to redo, we're going to find our last checkpoint. So this is the part where on failure we scan kind of backwards through the log to find our first checkpoint. And we're going to keep track of an undo list, the list of transactions that we will need to undo. And at the start we're going to say this list of active transactions at the time of the checkpoint, those are the ones that are sort of candidates for undo, that we might need to undo. So once we've found that checkpoint, we're going to scan forward we're going to scan forward from the earliest start among the transactions in this list. So we're going to go kind of above our checkpoint L and above our most recent checkpoint record, and scan forward kind of toward the end of the log from this earliest point. And as part of this scanning forward, when we see a record, so when we see some TI, X, R, V old, and V new, or when we see one of those redo only records, RTI, X, and V, on either of those, we're going to set We're going to write our v our v new to x. I guess these redo only records for consistency. I'll say this is the new value that was given to x at the point of this record. So we're going to scan through, see any of these updates, reapply them. So we're just replaying history here. If we see some TI start, we're going to add TI to our undo list. So if we see anything that started after the checkpoint, that's also something that we might need to undo that was kind of interrupted by this crash. And third, when we see a commit or an abort for some transaction TI, that's when we'll remove TI from our undo list. So this redo phase is serving two functions. It's generating this undo list where we're figuring out, okay, which of the transactions that have changes that may not have made it out to disk, which of these do we actually need to undo? And in order to figure that out, and also because we want to make sure that those that we don't need to undo actually have their changes reflected on disk as part of recovery, we're going to scan forward, reapply all of the updates we see, record any transactions that started after the checkpoint that we need to undo, and any that completed that weren't interrupted by our failure. Those we just want to redo. They aren't candidates for undo. And so once we get through this redo phase, we'll have restored the database to the state it was at when the crash occurred according to our logs. And one note about that, because we're doing write ahead logging, because logs always make it out to disk before the data does, it's possible that we would have changes where neither the log nor the buffer pool pages made it out to disk, and those were lost upon the crash. But that still follows our ACID guarantees in that that would affect the transaction would still be atomic. The database would still be consistent because atomic, because none of its effects would happen, and our kind of durable guarantee applies to transactions that committed. And if we have a transaction whose logs and data, none of them ever made it out to disk, then it never committed, and we don't provide the durability guarantee for uncommitted transactions. And so this redo restores our database to the state it was at the crash, and now we're ready to proceed to our undo phase. All right, for our undo phase, here we're going to, instead of scanning forward through the log, we're going to scan backwards through the log. So I'm going to scan backwards from the end of the log, and when we encounter one of these update records, we're going to write the old value to x. We're going to restore x to the old value. We're undoing this update. And at that point, we're going to append our record TI xviol, our redo only record, to the log to record that we did undo this, and in the case of another crash, we want to make sure that this is redone, and will ensure that x will have the correct value upon another recovery. And if we see a TI start, so if as we're undoing we get back to the point of the start of some transaction, this, well, as we saw before, we're going to append an abort record to our log to indicate that we have kind of successfully completed the undo of our transaction, and the state of the database and the state of the log reflect that it has been aborted and rolled back, all of its changes undone. And we're also going to, at this point, remove TI from our undo list. And that's something that I definitely is an important point, that this first one is only where our TI is in our undo list. So we're only, when we're scanning back, we're only undoing updates from transactions in our undo list. These are the ones that we need to roll back. And finally, we would stop our scan when the undo list is empty. So we're going to scan backwards from the end of the log until we have seen the start of all the transactions we're undoing. We've undone all their changes since they started, and we have finished our undo phase. And when we finish this undo phase, the database is fully recovered, and we're ready to resume kind of normal operations, allow new transactions to begin again. So this was sort of an abstract view of what these two phases are doing. Next, I want to go through an example of recovery and how both these phases would work. Okay, so here's the situation. We have our log. There are some older log records above here that I'm not showing, that aren't relevant, and we have three transactions involved here: T100, T101, and T102. And T100 and 101 started before our most recent checkpoint, and they were active at that point, so they're in our list L with that checkpoint. And then T2 started sometime after, and actually T100 began a normal abort before our crash, and actually rolled back the change that it made earlier and completed its abort right before we then crashed. So here we are in our crash, and we're going to do our redo phase. And the first step of the redo phase is to scan backwards until we see a checkpoint. Okay, here's our most recent checkpoint, and our undo list is T100 and T101, at least at the moment. And now we're doing our scan forward from the start of the oldest transaction in our undo list. So that's why we have to go further back to the start of T100 and scan forward from here to redo all our changes. So we'd redo updating B to 2050. We see T100 and T101 start, which would add them to our undo list, but this is before our checkpoint, they're already in there. We'd redo T101's change of C from 700 to 600. Then we see T101 commit. So that once we see that it's committed, we're saying, okay, it did successfully complete before the crash. We don't need to undo it. We'll take it out of our undo list. Now we see T102 start, So it may have been interrupted by the crash, so it is a candidate for undo. We'll add it to our undo list. We'll replay T102A change from 500 to 400. So if we're looking at our A right now is 400, B is 2050, C is 600 in our database. Now we see this redo only log, which was recorded when T100 aborted. So now it says, okay, B should actually be 2000. We'll do that. And we see T100 abort, so it completed before the crash. So the database as we have it now is consistent with the T100 log records that we have. All right, now we're at the crash. So we have completed our redo phase. We have restored the database to the state it was in when the crash occurred. And now we look at our undo list and say, okay, we do have something in our undo list, so we're going to scan backwards from the end of our log, undoing things related to transaction 102. So transaction 100, don't care, transaction 100, don't care, transaction 102. Okay, this we want to undo. So we're going to change A back to its old value, back to 500, and we're going to append our compensating log record or redo only log record for T102 resource A 500, and we continue scanning back. We see T102 start. So we've seen all the records from T102. We can get it out of our undo list, and finally we write a T102 abort to our log to record that we have kind of successfully rolled back all the changes from T2. Our undo list is empty, and we have completed our undo phase, and our database is fully recovered and ready to start running normally again. All right, so that's our our first look at a recovery algorithm. So there are a few issues with this, and the most pressing of which is our checkpoint strategy, our freeze the world, nothing can happen strategy. And in particular, if we have to wait for all transactions to finish running, what if we have a long-running transaction that's going to take 6 hours to finish? And while we're waiting for the checkpoint to start, we can't let any other transaction start. So we have to wait 6 hours for this transaction to finish, then do our checkpoint, and only after all that time can we allow the database to start new transactions. So that's just not going to work in a real system, and we're going to need something better. And this is going to involve a strategy called fuzzy checkpointing. So fuzzy checkpointing sounds cute and cuddly, and the whole idea is that we're going to allow updates during the checkpoint. So in order to not pay this huge overhead for our checkpoint in having to freeze all transactions, we're going to allow updates to happen. So how is that going to work? Well, it's not going to proceed without kind of any sort of freeze, but we're going to stop updates for just a short amount of time. So how our first step is kind of we're going to temporarily stop updates, and this will give us time to write our checkpoint log record and flush the log to disk. So we're going to stop updates for the time it takes to write one of these checkpoint records to our log and flush the log out to disk. And fortunately, our log is going to be much smaller than all the pages of data all the dirty pages that we might need to flush. So just flushing the log shouldn't take too much time, and it's going to not be too disruptive to stop updates during this time. And the other thing we'll do is do a scan through our buffer pool, and this is the pages in memory, so this is quite fast. But we're just going to scan through the buffer pool and just record which are the dirty pages. There's some set M that is all the pages in the buffer pool that are currently dirty. And at this point, we're going to allow updates to resume. And now that updates are running, we can do the slow part of the checkpoint, which is flushing all our dirty pages out to disk. So we'll go through the dirty pages that we saw at the time of the checkpoint and write all of those to disk. And we're going to need to ensure that any log records pertaining to that page are written out to disk first. And then the last thing we'll do is store a pointer to the checkpoint record, the one that we wrote in step 2 here, in a fixed kind of known position that I'll call last checkpoint on disk. And so what this will look like is we have our disk here, so our disk, and we also have our log, which also on disk and in memory, but our log has some log records, a checkpoint, some more log records, another checkpoint, and we have this last checkpoint pointer that it's pointing to the last checkpoint. And then we enter this process, we write our new checkpoint, and once all the dirty pages that we identified in step 3 here are written to disk, then we update this pointer to refer to the new checkpoint record. And so what this means is that that all the log records previous to this checkpoint that this last checkpoint refers to have their changes reflected on disk. All the log records that appeared before we appended this checkpoint, those are ones that made the changes that caused this set of pages to be dirty, and these are the set of pages that we're writing out. So it's possible that we would write out changes that were caused by records after this checkpoint, right? Because we're allowing updates to resume. So these pages, as we're writing them out, may have had other updates to them. But all the records before this checkpoint, we know they're on disk. So that's one thing that this gives us. And the second thing is, let's say we write the checkpoint, we identify the set of dirty pages, we allow transactions to resume, but writing all these dirty pages takes some time, and there's actually a crash while we're doing this step 5. And so this is a kind of an incomplete checkpoint. We wrote some of the dirty pages out, but not others. Fortunately, this is not a problem because we don't update our last checkpoint pointer until we have written all the dirty pages out. which means that if we have an incomplete checkpoint, then our pointer would still refer to an older checkpoint. We'd use that, and we'd be safe for recovery. We wouldn't have a checkpoint that claims that things were written to disk when they weren't actually due to failure. So this fuzzy checkpointing will reduce the overhead for our checkpoints. We will just have this kind of temporary stop of updates rather than stopping them during this potentially lengthy writing out process. So that's going to be an important win. However, we can do even better, and for this we're going to talk about the kind of gold standard recovery algorithm developed by who else? Developed by IBM, this time in the 1980s for their DB2 system. So I want to close talking about this algorithm that they came up with. So this still state-of-the-art recovery algorithm is called Algorithms for Recovery and Isolation Exploiting Semantics. And you really feel like the IBM people were very excited to have the acronym be ARES and just sort of strung words together until that happened. And so this, I'm not going to dive into every detail. It's an extremely extensive algorithm. There's a 70-page academic paper that they published with all the details, how to handle all the edge cases, how to recover from every scenario, and it includes kind of numerous optimizations. So I just want to give a high-level kind of picture of what's different about this algorithm, which is the one that DB2 and Microsoft SQL Server and others use, how it's different from what I've talked about so far. So there are a few major differences. The first is ARES uses something called a log sequence number, or LSN, to label and identify log records. So every record in the log will have a log sequence number, and they're just an increasing sequence of integers. So the first record gets LSN1, the next gets 2, the next gets 3, and so on. So that may not sound very useful. We have our lines are numbered, so why do we care about that? We can actually use this to kind of be smarter about which records we should look at, given information about kind of which records actually modified a page. So one way we'll use these is that each page is going to track two log sequence numbers called rec.lsn and page.lsn. And these will be kind of contained in the header of the page. So every page is going to keep track of these two. Our rec.lsn is only for pages in memory, and it is the oldest log sequence number that made that page dirty. So we bring a page from disk into memory. It's initially clean. There's some update made to data in that page, and that update goes in the log, and the log sequence number of that update becomes the rec.lsn of that page. So this kind of tells us how far back in the log to go to see the first update to the page that has not been written out to disk, right? Because this is for dirty pages. The page LSN is the LSN of the most recent update to the page. And this could be different for a dirty page in memory than the version of that page on disk, because the dirty page in memory has had updates that the page on disk doesn't. And what these two numbers give us is the rec.lsn and the page.lsn for a dirty page in memory. Tell us, here's the range of the log, an earliest LSN and latest LSN that are the range of the log where updates have been made to this page. And for pages on disk, they have this page LSN, which tell us what is the most recent LSN that was written out to this page. And so Aries can use these to be more efficient about kind of which updates have already been applied to disk versus which haven't, and can avoid redoing unnecessary work. So another important change is a particular kind of physiological logging that that a database using Aries does. And if you remember from the logging video, we had physical logging, where we're logging kind of the exact kind of bytes that changed with each update. We have logical logging, where we're just logging the SQL statements and nothing about the physical representation. And then physiological logging is some hybrid of the two. And in this case, we're going to log the actual page ID and potentially a slot number, basically the location, the page that was changed as a result of this update. So this would be something like we had TI, it changed page 1, 2, 3, and it changed page 1, 2, 3, say slot 2. So this is some particular tuple or location within this page, and it changed it from 500 to 600. So with this physiological logging, when we're logging the page IDs, now we can tell when we see updates in the log which page that involved, and because our pages now keep track of which records in the log actually modified them, we can tell, okay, this log record indicates that page 1, 2, 3 is dirty. This log record will actually have a log sequence number, so maybe its log sequence number is 4000. And so now we can look at page 1, 2, 3, say on disk, and say, is its page LSN greater or smaller than 4000? If the page LSN is greater than 4000, then it has then a more recent log record was written out. Well, a modification from a more recent log record was written out as part of this page, and so this one must also be reflected in that page, and we wouldn't need to, say, redo it. And so logging these page IDs is going to be part of what allows us to make these sort of optimizations. So 2 other quick points. We're going to for Aries is going to maintain this separate data structure called a dirty page table. This is distinct from the page table in the buffer pool. This is just a kind of a different map, a different hash table, where we're going to keep track of the pages that were dirty at the time of a checkpoint, as well as ones that we can see were made dirty by updates following a checkpoint. And in particular, this is again going to be part of kind of using these previous 2 points. It's going to be how we can tell, okay, which pages were actually dirty at the time of the checkpoint, and thus avoid redoing changes to pages that weren't actually dirty, that we know were already written out. And finally, I said that we could do better than the fuzzy checkpointing that I presented previously. And so this is going to be checkpoints where we don't require pages to be written out to disk at all. So checkpoints we're going to record which are the dirty pages, and the active transactions, and we're going to just we're going to make writing out dirty pages not part of the checkpoint process at all. There's just going to be some background thread that is scanning the buffer pool and kind of writing out dirty pages as the database system goes along. And all our checkpoints are going to do is just record the dirty pages and active transactions at a point in time. And this is all this information plus the log and the various log sequence numbers that we're keeping track of is going to be sufficient to determine what data do we need to redo and undo and what's already on disk. This Aries, we saw that the recovery algorithm that I previously talked about had two phases, redo and then undo. Aries is going to add a third phase. Its third phase is first, we're going to do analysis, then redo, then undo. What is this analysis going to accomplish? It's going to identify our undo transactions, just like our undo list from before. It's also going to find a redo LSN. So our analysis here is doing kind of parts of what our redo phase in the simpler algorithm was doing, where it was scanning through, and it was identifying kind of which transactions do we need to undo, and here our analysis phase is where we're scanning back to our checkpoint. We're identifying the transactions that started after the checkpoint. When we get to the checkpoint, we know what the active transactions were at that point, and because we're keeping track of these LSNs, we're going to be able to identify where in the log, which log sequence number do we need to start at for the kind of oldest active transaction, and then the redo and undo will proceed similar to the phases that I already described. And so Aries is going to be the one, is going to be the algorithm that kind of the high-end systems that want to kind of support really robust recovery that's both fast and very reliable. This is the technique that they'll implement. And there's more detail about some more specifics about Aries in the posted reading. All right. With that, I'll bring the lecture to a close, and I look forward to your questions. Oh, what's that? That's bird. The boy. The boy's in the bird. Ah!
Coming this summer, a terrifying new film, Alfred Hitchcock's The Void.